review, methodology, result discussion, and conclusions. And for my project background, same also. Nanoparticles are defined as material with size range of 1.
Boleh, jalan.
Okay.
So
my problem statement is that currently the usage of nanomaterial in industry has increased. So that's why, for example, in medicines, manufacturing environments, so most of the manufacturing units that process nanoparticles face a threat from fire and explosions. However, very few know about this threat, about how the fire and explosion happen when involved the nanomaterial. That's why I want to develop a dispersal model so that the risk assessment of the nanoparticle can be done and can be implemented. So next, project objective: to develop a dispersal model for nanoparticle using CXD simulation software, and to study the differences in dispersion behavior of microparticles and nanoparticles. So the scope of study for this project, I'm using aluminium nanopowder because aluminium is common material that used in industry, and it also one of the material that can cause explosions. And the project used the Enms fluid to model the dispersion of Enms with an Euler language approach. What means by Euler language approach is that Euler approach is that we set a boundary and we monitor the movement of material inside the boundary. So while the language is that we monitor the movement of specific material, specific particles. So we combine the approach. Okay, next, this is the literature review. Here, factors affected the dispersal behavior that have been studied by Enms. There are 3. For the first one is particle size, and this factor also have been supported by the other author, such as Lee et al. With their title of project explosion characteristic of nano aluminium powder and mixed in 2 liter spherical vessel. And they found that reactivity of aluminium powder was significantly higher for finer scale, which means in nano scale, compared to the larger one, which is in micro scale. Next is Vickness et al. With their research or project risk assessment of ignitability and explosibility of aluminium nanopowder. And they found that concerning the explosion severity characterized by the maximum explosion pressure and maximum rate of explosion pressure, it tends to increase as the particle size decreases or the specific surface area increases. And last one is a default et al. With their project ignition and explosion of nanopowder, something new under the dust. And they found that the explosion severity tends to increase as the particle size decrease or the specific surface area increase. So what we can conclude from this literature review or these studies, the smaller the particle, the dust ignitability increases as well as its explosibility. So the second one is the concentration of particles, and this also has been supported by the other authors, such as Bollet et al. With their project explosibility of microns and nano-sized titanium powder. And they found that optimal dust cloud concentration to produce maximum overpressure and rate of pressurize are lower than micron size. The next one is MEC, minimum explosible concentrations. It's generally independent for particle diameter because based on their research, for 100 for the optimal dust, for 150 nanometer of titanium, then it required about 500 gram per meter cube, and while the micro titanium required 1,500 gram per meter cube. So that the concentration for microparticle is higher compared to the nanoparticles. While for MEC, why it says that it independent for particle diameter? Because based on the experiment, the size of titanium of 150 nanometer material required 40 to 50 gram per meter cube, while microparticles needs almost the same, about 50 gram per meter cube. So that's why the MEC is independent for particle diameter. And for the next one is the Lee et al. With their title, with their project Explosion Characteristic of Nano-Aluminium Powder and Mixer in 2 liter spherical vessel. So they found that nano-aluminium powder's maximum explosion rate of pressurized was about 2 to 6.5 times higher than microaluminium. So what we can conclude that minimum explosibility concentration is independent of particle size, and the smaller the size of particle, the lower the concentration and the higher maximum explosion pressure. So next one is the agglomeration rate, and this has been studied by Bollet in their project Ignitions and Explosion Rings of Nanopowder, and they found that the material tend to agglomerate to each other when dispersed into the air. So when the material is agglomerate, so the total surface area increase, and this lead to the minimum or decrease the minimum initial energy, so that it resulted in higher risk of flammability and explosion, because the minimum initial energy has been decreases. So the chances or the risk to catch into the fire, to catch into the flammability is higher. So this is a methodology. So the first one, we need to create a geometry, and if you can see here, this is my geometry in a sphere shape, because in the experiment they use 20 liter spherical vessel. So that's why I need to create a geometry in a sphere shape. And next is the name selection and meshing. Meshing is the step where we divide the geometry into the smaller part. And this step is very important because we need to make sure that our meshing is in high quality. If not, it will affect our result. The result obtained will not accurate. So next is the CFD analysis and solution method. So for this one, for this step we need to specify what model we want to use. So for my project, I use two models, which are viscous model and discrete phase model. For viscous model, we choose the K epsilon model because this model is the commonly used, and it is popular because it is a good convergence rates and low memory requirement. While the discrete phase model it tracks the motion of individual particles, because we want to monitor the movement of particles. That's why we use these models. And lastly, we compute the solutions. So this is the machine. So next is the results and discussion. Okay, this is a result from the bullet, the time sequence of compute mass of turbulent kinetic energy. And for this bullet experiment, they use transition mode. Transition mode means that we can monitor the movement of material or the particle over time. So that's why we can see there is time here, 20 milliseconds, 7 milliseconds, and so on. So for my part, I use steady mode. So that's why we cannot. That's why there's no time here, because we cannot monitor the movement of particle over time. We can only obtain the end result of the dispersion in the steady mode, because supposedly I have to do in the transition mode, but however there are some difficulties, and after I discussed with my SB, so we changed to the steady mode. So this is one for the micro particles, and this one is for nanoparticles. The pattern is quite same, but the difference is the turbulent kinetic energy. So for the nanoparticle, the turbulent kinetic energy is higher compared to the microparticles. And I forgot to mention that the input that I got, the input for the simulation, mostly I got from the literature review, from the experimental that had been done by this Ali Benedetto and other other software. So for the discussion, based on the study by the Dispersal, the dust limiter, it found that the dust dispersion will become less uniform when the particles size is bigger. So that's why the turbulent kinetic energy for micro particle is lower compared to nanoparticles. It means that dust dispersion for nanoparticles is more uniform. So when it more uniform, the agglomerate rate is higher. So that's why when the agglomerate rate is higher, the explosion will occur. The possibility for explosion to occur is also faster. Next, so the conclusions: the dispersion model for nanoparticles have been developed using Z-ray simulation, so that with this model, it can assess. We can do the risk assessment for nanoparticle explosions. So that the objectives are achieved, the objective that I mentioned in earlier. So for the recommendation, conduct the simulation of dust dispersion for different concentration of particles, because when the particle is heavier, they might affect the dispersion of the material, maybe the flow of the material. And next is to study the dust dispersion with various discharge flow in transient mode. So if we conduct this study, we can know at what point the dispersion or the explosion can occur, because we use the transient mode. Because we use the transient mode, so we can monitor the particles and at what time the explosion can occur. So these references that I use. So this one. So that's all.
What is your result in this now discussion? Doesn't catch my attention. What is the significance there of your simulation that you showed just now? You just show the figures. So you did for, this is for what? Microparticle. Okay, then that one is a nanoparticle. So how does that,
Because the difference is between this one, the turbulent kinetic energy.
There is a minus sign. Minus sign means
Small.
Yes, it's small, but it's
small, which means that nanoparticle is smaller, isn't it? Minus
higher. So because
but that is, how significant higher is that? It's just at that level, it's the difference is negligible.
based on my calculation, about 20%
So
higher.
there's not really not much. In fact, there is, tak ada apa lah. Same lah.
Minus 7 juga.
Because that's why I want to, for the recommendation part, we propose to do the interaction mode, so that we can see when the point is the explosion can occur. Because suppose say, as I mentioned earlier, we have I need to do the transient mode. So because frankly speaking, that when I got this project, I totally do not familiar with the software. So one more thing, that the input for the simulation based on the literature review is not enough. The literature review only provide only I think 20 to 30% of the input. So the other rest we need to try and error. We need to do.
How do you model? How did you model? Did you start from scratch? You write your own?
Yes.
Your own line and everything.
Your own
Formulation. Your formulation is based on what then?
Or not? that's already the model. So we need to choose the correct model, because that's why I choose I mentioned that we choose the viscous model and discrete phase model.
Because why you use
Pardon?
CFD?
Yes, CFD is computational.
Why you use that? Is there any other software you can use, or can start from? Easier for you to once you know the model.
For CFD is the common software that used for the safety purposes. So by CFD we can determine the behavior of particles. Maybe this one of the